Okay, today we'll discuss about current electricity. First of all, we'll talk about DC, direct current, or DC voltage, let's say. If along the y-axis you have voltage and along the x-axis you're plotting time, if you plot pure DC voltage, you will get a straight line. What does that mean? That the DC voltage remains constant over time. Number two, you've studied in semiconductors, electronics, that we have something known as pulsating DC. Now here, this is the voltage, that is time, that is a pulsating DC. Even if one of the alternate cycles are not there, even then it is a pulsating DC. Why is it a pulsating DC? Is because you only have variation in the positive quadrant. There is no variation in the negative quadrant. So that is why it is called as a DC, and because it is varying, you call it as a pulsating DC. Then we have AC, of course. AC, you clearly have voltage here, time, if you have something like that. Now here, the voltage is varying in magnitude and direction with respect to time. Anything like that is your AC. Similarly, if you have something like that, that is also varying in magnitude as well as direction, so that is also your AC. Okay, next we want to write about what could be the current due to a revolving electron. If you have an electron which is revolving with velocity v in that direction in a circular path of radius r, then you can simply write the current as the charge upon the time. So we have the charge E and the time taken to complete the circular path, that is capital T, where capital T is the time period. Now time period, or the time, is the distance upon the speed. So if the distance is 2 pi r, the speed is v. So you have 2 pi r below and v will go up. So we have E v by 2 pi r. And I think you would agree that v by r is omega. So therefore you can also write I as E omega by 2 pi. Okay. Next we talk about current density. Now first of all, current density is a vector quantity. You normally write that as J vector. And J vector is defined as the current per unit area of cross section. I repeat, it is a current per unit area of cross section. And of course you have the vector quantity over here. So on the right hand side you write n cap, where n cap is a unit vector in the direction of current. So obviously the unit would be ampere per meter square. So if you have a conductor like that carrying current I, then that would be your n cap, and that would be the direction of the current density. Now what if you have a conductor which is like this, like that? So now if you consider this as A and that angle is theta, then obviously that would be A cos theta, and that would be your n cap or your J vector. So now the area of cross section is not A, it is A cos theta. So you can now write J vector as a current, which is I only, I upon A cos theta n cap. Great. Then we'll talk about drift velocity. Now we've had a discussion about this in great detail in our lower classes, but again, see, when you talk about a conductor, in a conductor, the charged particles, that is the free electrons, they are in a state of random motion, and the speed of that random motion is about 10 to the 6 meter per second. Okay, but that motion does not give rise to any current, because the motion is not in any uniform direction, it's random. Now to that conductor, if you give a potential difference, then the random motion will continue, because the random motion was in the first place not because of any potential difference. So if there is a potential difference, why should it stop? So it will continue, but that motion does not, like I said, give rise to any current. So now because of that potential difference, you will find that these charged particles, they begin to drift. If it is an electron, it will begin to drift towards the positive terminal, and the speed with which they drift is known as the drift velocity. And the drift velocity normally is of the order of 10 to the minus 4 meter per second. That is the range or the order of your drift velocity. Now, why in the world such a small value of current, and how in the world can such a small value of drift velocity can give rise to instantaneous current? That we've had a discussion in the 11th standard, where I had talked about a long hose pipe going all around the earth. If it is empty and if you open the tap on one end, then by the time you get water at the other end, it is going to take a few months. But if you have the tap already filled with water, and if you connect one end to a tap, then the water at the other end would be instantaneous. So same goes for a conductor. It is already filled with charged particles. So even this kind of velocity will give rise to a current. Now, if you consider a conductor like that, and you have charged particles everywhere, and you consider two regions like that, such that the distance between these two regions is x, and the area of cross section is A. Now we define a few things, but before we go ahead, we will not return back to this. What is the volume of this region? This distance is x and the area of cross section is A, so the volume of this is AX. So that much we agree to. Okay, now let us say n be the number of charges per unit volume. So in that region which we just have seen, what is the total number of charges? The total number of charges would be the number of charges per unit volume into the volume. And what is the volume? A into x. Now this is the number of charges, and if the charge value is Q, then obviously the total charge would be Q into the total number of charges. So it will be A Q N A X. So that gives you the total number of total value of charge. Now how do you define current? Current would be the total charge upon the time. So that will be Q N A X by T. Now X, if you remember, was, we have to go back here. X is this distance, okay, and T is the time, let us say, to go from here to here. Okay, so don't you think X by T would be the speed of the electrons, which is giving rise to current, which we have understood as the watt speed or a watt velocity as the drift velocity? So therefore X by T would be equal to Vd, where Vd is the drift velocity. So therefore you can write current I as Q N A V D. All right, okay. Now from here, therefore, can you write VD? as I by Q N A. And what do you think? 1 minute. Yeah, can you see? What do you think is I by A? It is J. So we have J by N Q. So that gives you the expression for drift velocity. Please remember this. Okay. Now we define something known as relaxation time. Now if you have a conductor over here, all right, and the charged particles, they are in a state of random order, all right. So if you have a charged particle, this is a positive end, this is a negative end, it is drifting in that direction. Now what am I showing over here? See, when it is going from here to here, let's say it collides with a positive ion, then it collides with another positive ion, then another positive ion, another positive ion. So it will keep colliding, you know. The average distance between any two collisions is known as the mean free path. So lambda you define as the mean free path. Okay, and the speed with which they are moving, we will write that as VRMS. That is the average speed. So therefore you define the relaxation time as tau. So tau would be what? The distance upon the speed. So distance is lambda. Speed is what? VRMS. Please remember this. That is the expression for relaxation time. Now, when you have a charged particle which is in presence of a potential, so there would be an electric field. So if there is an electric field, then there would be a force acting on it, and that would be F equals charge, let's say is an electron, so it will be E into capital E, which we can rewrite as MA E capital E. So therefore we have A as E by M. Now we are talking about charged particles which is moving and giving rise to the current. So the speed with which it is moving is the drift velocity. So the acceleration will be Vd by time, that is a relaxation time. So therefore what we have Vd as? Vd will be A into tau. A is this, so it will be E capital E M tau. So that gives you an expression for drift velocity. But if you just go up, here, do we know that J is equal to NQ into Vd? So coming back, since J equals NQ into Vd, or rather NE into Vd, so we can write J as NE. Vd we will write here, so it will be E capital E tau by M. So do we get NE squared capital E tau by M? Let us rewrite this. So we'll write J equals NE squared tau by M capital E. Now this term is a constant, and that constant is written as sigma, and that sigma is NE squared tau by M, and this sigma is conductivity, which is equal to 1 upon resistivity. So therefore, can you write resistivity would be M upon NE squared tau. So rewriting this, could we now write, therefore J as sigma E. This is your Ohm's law. This is Ohm's law in terms of current density and your electric field. Okay, please remember this Vd, the various expressions that we have derived, write them down separately. The derivation of course is only for you to understand. Of course, you don't need to remember the derivation, but you need to actually remember these values, this formula, because they are going to be helpful when you're talking about an all India entrance examination. CET, no. All India, possibly. Okay. Next, we'll talk about the temperature dependence of resistance. This also we know. We remember this expression, RT is equal to R naught 1 plus alpha T, where alpha is the coefficient of expansion for resistance. T is the increase in temperature. R naught is the resistance at 0 degrees Celsius. Now this is when a temperature or when a substance has a positive temperature coefficient. That means as temperature increases, the resistance also increases. If there is a negative temperature coefficient, for example a semiconductor, then you'll write RT as R naught 1 minus alpha T. Now please remember, both these are valid for a temperature which is less than equal to 300 degrees Celsius. For temperature which is greater than 300 degrees Celsius, the RT is R naught 1 plus alpha T plus beta T squared. This is another constant which will be given to you if that case is there. Similarly, RT would be equal to R naught 1 minus alpha T minus BT squared. This is of course for PTC, this is for NTC. Okay. Next we go for stretching of a wire problem. If you have stretching of a wire, so if you have a wire of length L1 and radius is R1, it is stretched and the length now becomes L2 and the radius becomes R2. Now from here to here, if this is V1, that is V2, the volume will remain the same. So we write V1 equals V2. What is V1? Pi R1 squared L1 equals pi R2 squared L2. So therefore we have R1 squared by R2 squared is L2 by L1. Now, do we know that resistance can be written as R equals rho L by A, that is rho L by pi R squared. So therefore R1 by R2 would be L1 by L2 R2 squared by R1 squared. Over here, don't we write R2 ulta agar kiya to R2 squared by R1 squared will be L1 by L2. So we'll have L1 by L2, L1 by L2. So therefore R1 by R2 is L1 squared by L2 squared. This is a shortcut formula. Please remember this. Okay, next, if you consider a circuit, like this, this is the external resistor having resistance R, that is a battery having internal resistance small r, carrying current I. So this is E, this is small r, that is your battery. I think you can write I as E upon R plus R. Now we can write power as I squared capital R. So we have power as E by R plus R the squared capital R. Now there is something which is known as maximum power transfer theorem. Proof not required, just see what the theorem is. This states that if the external resistance R is equal to the internal resistance, then maximum power is delivered. So for P max, we have small r equals capital R. Using this over here, if you do the requisite math, you will get P max as E squared by 4R. So that is a formula for maximum power, and I'd like you to remember that. Okay, now we'll talk about something a little more advanced. This is normally done in electronics or electrical engineering, but it is a shortcut which will help you a lot, and I'll tell you how. This is known as the delta to star conversion. Before we go ahead with this, first of all, we'll talk about something which is known as a T network to a star network. What is a T network? You have a resistor here, P. You have a resistor there, Q. You have a resistor here, R. And let this point be 1, this point be 2, this point be A, this point be 3. Then if you convert this to a star network matlab Y ki taraf, then it will look like this. It's not difficult. If you just apply your brains, you will understand how it is like this. This is 1, this is P, this is Q, this is R, this is 3, this is 2, and this is A. Okay, this was T network to star network. Okay, now if we talk about a pi network, to a delta network. What is a pi to a delta network? If you have a system like this, that is 1, this is 2, this is A, this is B, this is C. If you convert it to a delta network, it would be like this. Okay, where this will be 1, this will be 2, this will be 3, this will be A, B, and C. Okay, so now we have done the T network to star network, pi network to delta network. We will now talk about the actual thing. That is what we really wanted to do, something known as the delta to star network. Let us see what this is. The delta to star network. So if you have a network like this, where this is A, this is B, this is C. Okay, let this resistance be RA, that be RB, and that be RC. Now you can convert this. This looks like a delta, no? So you can convert this to a network which appears like that, and which you would agree is much simpler for solving as compared to this in a network. We will see in a short while, where you will take this as R1, this as R2, this as R3, this is A, this is B, and that is C, where you have your A, B, C. So in place of your A, B, C, you have A, B, C. In place of the cyclic network like this, you have a star network like this. How, what is the value of R1, what is the value of R2, etc. We will just find that out in a short while. We'll do the requisite mathematics. Now, sabse pehle, let us consider this. Now, if you consider this, you want to find the resistance between A and B. So you want to find the equivalent, forget about this now. Let us focus here. You want to find the resistance between A and B. So would that be RAB? Now in between this, don't you think this would be parallel to this and this, where these two are in series? So RA would be parallel to RB plus RC. Similarly, you want to find the resistance between B and C. So RBC mein RC would be parallel to RA and RB. Similarly, RAC mein RB would be parallel to RA and RC. So keeping that in mind, I will just write one term, and the remaining two terms it will follow. So we will simply write now over here that for RAB, we have RA parallel to RB plus RC. So therefore you have RAB, it will be, if you solve it, you will get that as RA RB plus RC upon RA plus RB plus RC. So if you simplify that, you will get RAB as RA RB plus RA RC upon RA plus RB plus RC. Similarly, now you know what the mathematics is. If you do the mathematics, you will get RBC as RC RA plus RC RB upon RA plus RB plus RC. Similarly, RAC would be RB RA plus RB RC upon RA plus RB plus RC. Let this be equation 1, 2, 3. Now, this is for the delta network. Now, let's talk about the star network. If you have the star network, if you want to find out RAB, that means the resistance between A and B, where this end, let us say, is open. So if this end is, one second, you don't have enough light. Okay. Now, if this end is open, then the resistance between A and B, this will not be there. Then R1 and R2, they are simply in series. Alright. Similarly, if you're talking about between B and C, then these two are in series. If you're talking about A and C, then these two are in series. This end is open, so that is not important for us. So this was, the above was for the delta network. This was for the delta network. We will now talk about the star network. So for the star network, we can write RAB as R1 plus R2, RBC as R2 plus R3, and RAC as R1 plus R3. Okay, this is equation 4, this is 5, and this is 6. Now just see, is this RAB? Is this RAB? Can you equate 4 and 1? Can you equate 5 and 2? Can you equate 6 and 3? I'll just equate 4 and 1, and I'll show you what it will look like. It will look like this. R1 plus R2 will be RARB plus RARC upon RA plus RB plus RC. Similarly, you can write for R2 plus R3, that will be equal to RCRA plus RCRB upon RA plus RB plus RC, and likewise R1 plus R3 will be equal to RB RA plus RB RC upon RA plus RB plus RC. So this would be equation 7, 8 and 9. Now you have to solve 7, 8 and 9. When you solve 7, 8 and 9, which we will not do, that if you want you can do, we don't need to do that. If you solve 7, 8 and 9, you will get you will get R1 as RA RB upon RA plus RB plus RC. ये ध्यान में रखो, अभी यूज करेंगे हम लोग. R2 will be equal to RA RC upon RA plus RB plus RC, and R3 is equal to RB RC upon RA plus RB plus RC. You know what this means? This means that if you have a network which is like this, this can be converted to a network which is like this, where the value of R1, that means if I simply draw this R1 over here, this is R1, this is R2, this is R3. So what will be the value of R1? R1 देखो क्या है उधर, RA RB upon RA plus RB plus RC. That means R1 will be RA RB upon RA plus RB plus RC. R2 will be RA RC upon RA plus RB plus RC. R3 will be RB RC upon RA plus RB plus RC. That means just the opposite sides को लेना है तुमको, and you can very easily do it. Okay, so this is when you are converting, and of course we are going to solve a sum, 2 or 3 sums, and then we'll see how and why have I done this. Now this was conversion of delta to y. Similarly, there is something which is known as conversion of y or star to delta. Star to delta में I will just do one, rest of course if you want, you are interested, you can do it. No, I'll only do it. So if you have R1, you want to convert to that. So R1, if you want to convert to that, that means you want to know what is the value of RAB. No, ये network है तुम्हारे पास, इसमें से वहाँ जाना है तुमको. तो अगर इसमें से वहाँ जाना है तो तुमको RAB चाहिए. इन दोनों के बीच में रेजिस्टेंस क्या है वो चाहिए, मतलब बेसिकली RA चाहिए. सो RA ये क्या है, R1 के ऑपोजिट में क्या है, R2 R3. वापस देखो, you want RA का value. If you want RA का value, then first of all you will write R1 R2 plus R1 R3 plus R2 R3, ये तो हो गया. And then R1 के, एक मिनट, हाँ, इसके we are converting A RA, sorry, correct. So we are converting star to delta. So this to this, that means this, इसके opposite में क्या है, R3. So over here it will be R3. Similarly, if you have, let's say, RB. So RB में ऊपर वाला term same ही रहेगा, R1 R2, R1 R3, R2 R3 upon RB ढूंढो, RB किधर है, RB इधर है. So if this is RB, इसके opposite में क्या है, R2, तो नीचे आएगा R2. Similarly, RC. So RC के लिए first term numerator same, R2 R3. Where is RC? RC is over here. So if RC is over here, opposite to that you have what, R1. So that is how you convert a star to a delta. You convert a delta to a star by these equations. Okay, now let us solve some sums, and then the idea will be cemented. Okay. What if you have a network which is like this? Okay. This is A, that is B. This is 6 ohm. This is 14 ohm. This is 4 ohm. This is 10 ohm. This is 2 ohm. Question is find the equivalent resistance. सबसे पहले whenever you are given a circuit like this, most of the time, at least in CET, it is a Wheatstone's network. Now here it is definitely not a Wheatstone's network. 6 by 14 is not equal to 4 by 10. So it is not a Wheatstone's network. So if you really do by the 12th standard method, what do you have to do? You have to solve Kirchhoff's law. Use Kirchhoff's law in this loop, that loop, external loop, do the requisite mathematics and then suffer, basically. So what do we do here? If by using the star delta method, is this a delta? Can I convert that to a star? So if I convert that to a star, it will be like this. A resistor here, a resistor there, a resistor here. So let us call this resistor as R1, this as R2, and this as R3. Let me draw the equivalent circuit first. Then you will understand how it simplifies. So this is your A, that is your B. In the upper part you have this now, okay, then you have that, then you have that, and the lower part will remain the same. So what is this? 14. This is what? 10. This is your R1, this is your R2, this is your R3. This becomes simple. How? These two are now in series, these two are in series, this and this parallel, and this parallel network is in series with that. Done deal. You can simply do it. Now what? You have to simply find the value of R1. R1 के लिए याद कर, ये अगर R1 है, it will be this into this upon this plus this plus this. याद है ना? वापस सोचो जरा क्या बोल रहा हूँ मैं. It will be this into this upon this plus this plus this. So R1 is 4 into 6 upon 4 plus 6 plus 2. That is 24 by 12. That is 2 ohm. So R1 is 2 ohm. ये हो गया. दिख रहा है? Now R2 देख लेते हैं because we will have to go down. R2 के लिए कहाँ गया R2? R2 is 6 and 2 and R3 is 4 and 2. So R2 is 6 and 2. So R2 is 6 into 2 upon the same thing 12. So that will be 12 by 12, which is 1 ohm. And R3 will be 4 and 2. So it will be 4 into 2 by 12, that is 8 by 12. So it will be 2 by 3 ohm. So now what? You know what is R1, you know what is R2, you know what is R3, this you know, this you know. Find the equivalent resistance using this. So what did you do? Simply you converted this delta to a star. In 2 minutes you got the answer. So that is the benefit of using the star delta method. Another sum, and number 2. Let us give you a homework. Similar sum only. In place of 6, you take it as 10. Just keep adding 2 to the everything. To everything add 2. So in place of 6, you take 8. Over here 16. Over here 12. Over here 6. Over here 4. Do the same sum. Get the answer. Next sum, number 2. What if you have a network which is like this? Now this is a fused network. I'll tell you what that is. This is A, that is B, and you have this is 9 ohm, this is 9 ohm, this is 9 ohm, this is 6 ohm, 6 ohm, and 6 ohm. Question is find the equivalent circuit. Now you will break your head. You do whatever you want using Kirchhoff's law. It will not take you less than at least 1 hour to get the answer over here. So what do we do is the external, let us mark this point as A. We already have a A. This is P, Q and R. The external delta network of P, Q, R of 6, 6 and 6, we want to convert that to star. So let us see how that helps us. So here we have P, we have Q, we have R, we have 6, 6, 6. We want to convert that to this. This is R1, this is R2, this is R3. What is R1? R1 ये R1 है, तो this and this, so 6 and 6 सब जगह same ही है, so it will be 6 into 6 upon 6 plus 6 plus 6, so it is 6 plus 6 plus 6. So R1 is 36 by 18, that is 2 ohm. सब कुछ same है तो सब जगह 2 ही होगा. So this will be 2, this will be 2, this will be 2. मतलब यहाँ देख अभी बाहर वाला निकल गया. So between P and Q and R, you will have a star-like network of 2, 2 and 2. So if you redraw it, it will look like this now. We have A, B, this is P. So you have the 9 ohm here, 9 ohm, 9 ohm. Okay, and this is Q and this is R. Okay, now yes, so now you have 2, 2, 2. So here you will have a 2, 2 and a 2 ohm. So we have a 2 ohm, 2 ohm and a 2 ohm resistance. Correct? So that is how you will have to actually solve it and get the answer. So here these two are in parallel, 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 and then eventually in series get the equivalent resistance. Solve it and get the answer. Okay. Remaining, I think, as far as this chapter is concerned, these are the only two numericals that I have thought about, because this is something which you have not seen about before. सिर्फ इसको 2-3 बार revise कर लो. The formula should get ingrained in your mind. Try some sums which are there in n number of books that you may have available using this method, and you will get the answer in minutes. Okay, sure. Thank you very much. Bye.